So I think we should get started. So good morning, everyone. Welcome to this morning's session. Our speaker is Marika Taylor, and she's going to be telling us about asymptotic fluxes in holography. Thank you.
Thank you very much, and apologies for the technical problems. So I'm going to talk about asymptotic fluxes in holography. Before I do so, a couple of comments on my institution. So my day job is as the Vice President for Engineering and Science at the University of Birmingham. I mention that in the context of interesting ongoing geopolitical events. If you know people who are stranded, bear in mind that I have a 350 million euro a year budget and could potentially be in a position to help them. So that's a general comment. So my group still sits primarily at the University of Southampton, although at Birmingham we're very much building up the supersymmetric quantum field theory side of the group. So we've got Daniel Brennan coming, we've had Lakshya Bhardwaj start with us recently, Andre Constantin as well. So it's a kind of a growing group. And my third day job, just to keep me busy, is with the Alan Turing Institute, which is the AI Institute in the UK, because a lot of what I do these days is related to AI, and I work with DeepMind there. So with that preamble, so let me tell you what I'm going to be talking about today. So I'm really going to be talking about conserved charges and fluxes in the context of holography. I'm going to be doing so really in the context first of holography, which in the better known context of non-zero cosmological constant. And in the end, I'm going to give you a preview of work which is in progress on taking the zero cosmological constant limit. And I'll be linking to some of the talks that we've seen here. So this is a sort of, I'm very much aware that we've got an audience full of experts and then some who've been following the field less. This will be kind of quite self-contained, and I might skip over some parts depending on time, given that we've got so many experts here. So gravitational theory, as we all are aware, observables are typically defined at the asymptotic boundaries. We are most familiar with discussing conserved charges, and in the context of holography, that's been the thing that we've focused on considerably. But in the context both of flat holography and in the context of cosmological spacetimes, we clearly need to talk about radiation. We need to think about things which capture the flux of gravitational wave going through the boundary. So what we're going to do is build on the covariant phase space approaches that developed by Wald and collaborators. But the thing that we're really bringing in from holography is deep understanding of the regularization and renormalization of infrared volume divergences, which we've obtained through ADS-CFT. So I'm suppressing the details of the latter through the talk, but that's an important thread in terms of the technicalities of what we're doing. So ADS, the canonical picture here, we've got a space-time boundary which is time-like, and that describes the background geometry for the dual CFT. It's very familiar to all of us that we define charges at the conformal boundary, and these are finite and these are renormalized using counter terms which are covariant with respect to the boundary. So this is a story that goes back 25 years. Now, both in more recent times and actually sort of in the literature, there are sort of discussions in ADS-CFT, even in ADS-CFT, of radiation going through the conformal boundary. So for many contexts in ADS-CFT, that is not the boundary condition that we apply. We instead have time-independent boundary conditions, we have duration boundary conditions. But we can consider the case where we have radiation reaching the conformal boundary in finite proper time, and this has been studied. And it's important to note here that typically in that case, the boundary conformal structure will be time-dependent. And if you look at the picture that I'm showing, the green is obviously the radiation. The charges are at most piecewise constant. So if you think about charges which are defined on the slices C1 and C2, clearly we've had fluxes that go through, there will have to be changes in them. And so even in this context, it's very natural to think in terms of fluxes and changes in charges between time slices. Now, that understanding, which goes back in the literature sort of 15, 20 years, becomes essential when we think about what to do in de Sitter. So de Sitter, again, a very canonical picture. So all of the subtleties of fluxes and charges in de Sitter spacetime. So these are all very, very well known. The first thing is that, you know, there's clearly no notion of mass in de Sitter because we've got no global time-like killing vector. If you want to have a mass, you'd need a global time-like killing vector. We don't have that. We have compact spatial sections, but at the same time, we have infrared divergences, which are now associated with divergences of future and past, so divergences in time. Whilst this isn't the focus of this particular meeting, understanding fluxes and charges in de Sitter and more generally asymptotically de Sitter cosmology is clearly important for the real world. It's clearly important in the context of inflation. It's clearly important for gravitational waves and cosmological background. It's actually genuinely really important in the context of, say, the LISA experiments, which are coming up in the next decade. So some of what I'm going to be talking about here actually picks up this case. And the reason I'm going to focus on this case as opposed to the ADS case is, firstly, I think it's less familiar. Secondly, some of the subtleties that we're ironing out, they are subtleties that haven't been resolved in the literature. And thirdly, this is a case where we naturally have dynamic behavior and we naturally have radiation. And it's quite interesting from a physics perspective to think about what we do in this context before we think about zero cosmological constant limits. In practice, when we take the zero cosmological constant limit, we will take it from the ADS case rather than the de Sitter case. But nevertheless, there are interesting lessons that we learn from the de Sitter case. So what we're going to do, as I said, is explore fluxes and charges, and fluxes in particular in spacetimes with cosmological constants. We're going to discuss what they mean. And then at the end, as I said, I'm going to give you some implications for asymptotically flat spacetimes connecting with the recent literature by taking the lambda goes to zero limit. So some of what I'm going to do is just picking up some of the things which were already in publications from a couple of years ago. And then, a lot of the talk is ongoing work with Aaron Poole, a former student of ours, now a postdoc, and Kostas Skandaris. I won't really touch on it too much, but there's also sort of parallel work in progress with another student, Arvind Shekar, which is around asymptotic observables. Just a note here, I will mention sort of various references throughout, but there have over the last sort of 5-6 years been complementary approaches to cosmological charges. I'll mention them as we come through. So the groups of Ashtekar and collaborators, Piotr Kreshel and collaborators, Bob Walden Code, Jeffrey's group, Jeffrey's collaborators, and many more. And I apologize if I'm missing out anyone in this room. I promise that it will be in, referenced appropriately in the paper. Okay, now in this particular audience, I don't, you're all or almost all very familiar with covariant phase space formalism. So I'm going to sort of zoom through this quite quickly, but actually sort of picking up on the elements which are really important for what follows in terms of what we do in ADS, de Sitter, and the flat limit. So the basic principle of the covariant phase space formalism. So we're going to start with a gravitational theory described by a diffeo-covariant Lagrangian deform. I mean, throughout this talk, I'm going to stick with Einstein gravity with cosmological constant. Adding other fields is absolutely completely straightforward. That's no problem at all. And of course, for cosmological or other applications, you often want to have scalar fields as well. So you've got your Lagrangian deform. And then important quantity, which is defined from this, comes from the on-shell variations of the Lagrangian. So the on-shell variations define for us the symplectic potential, the -1 form, which is defined in terms of the metric or the fields and their variations. So this is the symplectic potential. And just to remind you what this is for Einstein gravity with cosmological constants, I won't use these expressions through the talk, but just to sort of explain that you can write this down straightforwardly. The symplectic potential is expressed in terms of the metric and the metric variations. You can see it's expressed in terms of the covariant derivative of the metric variation. And again, if you wanted to generalize this to add more fields or even to do higher derivative, it's very straightforward to do. So that's the symplectic potential. Now, the really important object for this particular discussion is going to be the symplectic current, which is the anti-symmetrized variation of the symplectic potential. So this is written again in terms of the field and the fields and their two variations, and again, an anti-symmetrized combination. So the symplectic current is closed on shell. So we're now going to restrict to the case of interest in which both the fields and their variations are on shell. So we've got this symplectic current. So from the symplectic current, using the fact that it is conserved on shell, we can start to define Wald Hamiltonians. So for a generic vector field, the Wald Hamiltonian, which is associated with a vector field, is defined as this function. It's defined such that the variation of the Hamiltonian is given by the integration of the symplectic current, which we defined on the previous slide, over a d-1 dimensional slice. So the symplectic current given by the field, the variation of the field, and the Lie derivative of the field along a vector field. Now, this kind of expression, when we see this expression and we see a d minus one-dimensional slice, our minds want to jump to this being a Cauchy slice. We're used to doing this on space-like surfaces. If you go back to the literature from 30 years ago from Wald, there was no such restriction. And in fact, in the original papers by Wald and his collaborators, they gave a number of examples where the d minus one-dimensional slice used was not a space-like slice. So this is, there's precedence in the literature. And so one can set this up, in more general contexts. And you need to define, for the physical context, what is the appropriate d minus one-dimensional slice. I emphasize that because I think this is one of the, the first lessons or the key lessons which comes through when we start thinking about cosmological spacetimes. Okay, now, how do we go from the Wald Hamiltonian into Noether currents and Noether charges? Well, if we've got a diffeomorphism, we can associate the d minus one form Noether current. We can express it in the form given, and here I psi contracts the vector with the first index of the Lagrangian D form. Again, it's straightforward to show that J is closed on shell and it's locally exact, and it can be expressed therefore in terms of a d minus two form Noether charge. So this is all, again, very, very formal and very familiar, hopefully, to most of you. Now, there are several important things about the Wald Hamiltonians. There are, throughout this talk, an enormous number of technical subtleties, and I'm only going to go into them where they actually play an important role for the physics. But there's an important question about when is the Wald Hamiltonian actually integrable? So we've defined it in terms of the variation as in terms of the formula which is given there. But of course, you can actually only integrate this equation to obtain the Hamiltonian if the right-hand side is a total variation. The first term written there is clearly a total variation, but the second term, in order for it to the integrability to be satisfied, that has to be a total variation as well. So that's an important condition. It won't play it will be playing a background role in the discussions today, but that's an important condition on the Wald Hamiltonian if you want to integrate it up to have a charge. Yeah.
Well then, thank you.
At this point, I'm completely agnostic about
agnostic, right? It's a completely general diffeomorphism. In particular, it's not symplectomorphic, right? It doesn't preserve the symplectic form.
Absolutely.
Okay, thank you.
I'm completely agnostic at this point. And that's quite important for me because I'm only going to put in restrictions when I physically understand why I'm going to put those restrictions. And again, just to sort of jump ahead, I'm going to be considering at various points in this talk cases where the psi is not a symmetry, which is which is more unusual compared to the literature. Okay, now the really, really important one for us in this context, I'm just checking. Okay, the really important sort of point for us in the discussions today is the point about conservation. So the picture on the left-hand side, I'm showing you here a picture of ADS, asymptotically ADS, you can see. I've got two space-like slices, C1 and C2. And each of those slices, I'm defining my Wald Hamiltonian. And I can compute the difference between the Hamiltonian and these two different slices in terms of omega. And the difference between the Hamiltonians on the two different slices is given by the integral of omega over a hypersurface whose boundary is the boundary of C1 and C2. So it's the green surface shown here. Now, this is a really important condition. So, it's something that we implicitly use all the time. So if we talk about charges being conserved, so we talk about, an ADS black hole, and we say that it's got a conserved mass, a conserved angular momentum, we're implicitly using the fact that, the Hamiltonian, which is used to compute that particular charge, is actually independent of the slice. It will only be independent of the slice if omega vanishes on B12. Now, of course, you could say at this point, well, hang on, could I just not just integrate omega over B12 and it could be 0? Of course, you can accidentally have them being equal, right? You can accidentally have that vanishing, but for it to generically vanish, you actually, for all positions of C1 and C2, you have to have omega being 0. Sorry. Okay, now the other thing, so before I go on, this is going to be a really important formula. So, I mean, remembering the details of the definition of omega, you know, the symplectic current is not particularly important, but the fact that the symplectic current controls whether there is actually conservation of charge is important, and we'll come back to this formula repeatedly. Now, as well as the fact that I've been completely agnostic so far about the vector, I haven't insisted that it's associated with a symmetry or an asymptotic symmetry or anything like that. It's really important that so far my discussion has been quite agnostic about the nature of these codimension 1 surfaces. So I've already said that in the context of ADS, we will typically be considering space-like slices, and the boundary of that slice will be the intersection with the conformal boundary. But actually, the key point that we're going to come to is that in the de Sitter case, the natural slice to consider in terms of charges is not a space-like slice, it's a time-like slice. And I think it's fair to say that that point has only been fully appreciated in the literature over the last 5 years or so. So if you go back in the literature, for a long time, people were trying to define charges in de Sitter through spatial slices. They ran into all kinds of subtleties and difficulties. The natural way to define charges is associated with time-like slices. And we're going to go into that and discuss why as we go through this talk. Okay, so that was a sort of lightning review of the covariant phase space formalism. And again, the key thing that we want to take from this is that the Wald Hamiltonians, the conservation of the Wald Hamiltonians is controlled by the symplectic current. So now let's jump over into ADS. So as I said, asymptotically ADS, we define conserved charges on space-like surfaces. The canonical example that we're all very familiar with is that we have a conserved mass if we've got a killing vector, time-like killing vector. But more generally, and this is a point that's going to come through into the entire discussion, including when we go to zero cosmological constant, the understanding that came through ADS-CFT was that actually we can impose very general conditions, asymptotically locally ADS conditions. And with asymptotically locally ADS conditions, if you go into Pfefferman-Graham form of the metric, as you go to the conformal boundary, you've got the systematic expansion, which Charlie and Robin sort of worked out over 30 years ago, this expansion, radial expansion of the metric. And there's this natural interpretation of these, the terms in the expansion in terms of the properties of the dual CFT. So G0 is a generic background metric for the dual CFT. The only thing that you need to require here is that it is non-degenerate. And G3, we're implicitly here in this talk in 4 dimensions, that's characterizing the state in the CFT. So this is, I think, familiar to everybody. Now, in the context of charges, if we're working specifically in asymptotically ADS, what we're saying is that we've got a space-time which actually converges as you go to infinity to ADS. We've got associated asymptotic symmetries. The asymptotic symmetries are in particular associated with the conformal group. And we're usually interested in the case where the psi, the vector that we choose, is actually an asymptotic conformal killing vector. And zeta is, which I'm going to define in a moment, is the associated conformal killing vector of the boundary G0, right? And so in particular, when I talk about sort of computing the mass, we're actually saying that in the boundary is just a flat metric. You actually have a time-like killing vector, and we're actually computing, that's one of the conformal killing vectors of the boundary, and we can compute the associated charge with that. And in particular, if we go through, so I said I was going to suppress all of the details around the renormalization and systematic treatment of renormalization, but in particular, in asymptotically locally ADS, we have a correspondence between the G3 term, the normalizable mode in the metric expansion, and the holographic stress tensor, and we can write all these conserved charges in terms of integrals over the boundary of a space-like slice in terms of this G3, which is the holographic stress tensor, and the boundary conformal killing vector. So these are, again, very familiar expressions. And the point is that the integrability condition for the criteria for the charges associated with the symmetries is automatically satisfied. So you can just go through the calculation and you can show that omega indeed vanishes on the conformal boundary. And that's the formal proof that the charges are independent of the choice of the slice C. So this was done, in a number of papers 20 years ago. I mean, included some papers by Papadimitriou and Skenderis, but other groups were also sort of showing these things. So this is, well-known story. Now, the part of the story which is known, but perhaps not so well known, is the following. Although we typically are interested, the most frequent case of discussion in the ADS-CFT literature when we're computing charges is the case where G naught is conformally flat. So it's typically something like we have a black hole and we're asking about the charges of the black hole. There is no reason a priori to restrict G naught to be conformal flat. The only thing that we need to say is that G naught is non-degenerate. So in particular, there is no objection in principle to G naught being time dependent. Okay, so we can have boundary conformal structure, which is time dependent. In this case, G naught is not conformally flat. And, if something is time dependent, by definition, we do not have a time-like killing vector. More generally, we may not have any killing vectors. We may not have any form of killing vectors. Now, we can nevertheless still set up charges and fluxes in this particular case. What I'm going to do in this talk is actually go through into the de Sitter case, because I think it has some interesting sort of lessons. But the examples explored in de Sitter link very much to the examples which were explored in ADS. So if you look at this picture here and think about what's happening. So again, the boundary here is, the vertical axis is just the conformal boundary. We're considering, again, space-like slices. But we're thinking of a situation where radiation is coming out into, reaching the conformal boundary. And what we're saying is that typically this means that G naught will not be conformally flat. In the way that I've drawn this picture, actually I've shown sort of quite a burst of radiation hitting the boundary. And you could say that actually when you come into, the lower sections of the boundary and the higher, the past and the future, it may be that G naught is actually conformally flat. And so asymptotically, we actually have conformal killing vectors. But temporarily, we have, over a finite period of time, we have radiation hitting the boundary and G naught becomes time dependent. And so what we can do in those contexts is actually explore how there are changes between charges between the slice C1 and C2, and we can calculate how that links to the fluxes going through the boundary. As I note here, there are some particularly interesting analytic examples which are studied in the literature. And in particular, Robinson-Troutman are particularly nice examples because they have this feature that actually there's radiation that approaches the conformal boundary, but actually at late times, Robinson-Troutman settles down into a Schwarzschild black hole. So at late times, you actually get, it approaches something which has symmetry. So the exploration of Robinson-Troutman, that goes back to a paper of Backus and Skenderis about over 10 years ago now. But actually linking to the more recent literature where people have been thinking about radiation going through radiation in ADS and the corresponding lambda goes to zero limits. I know that many people in the room have been thinking about this, and we'll come back to this a little bit later. So I'm going to go on now to discuss de Sitter charges and physical interpretation. So from a technical level, throughout this talk, I'm going to be completely agnostic about a CFT dual to de Sitter. I'm not actually going into that in detail. What I'm doing is actually learning from ADS-CFT and the analytic structure that we have there. I'm learning from that in order to define asymptotic charges and fluxes for de Sitter. The charges and fluxes we set up may have a wonderful interpretation in terms of a dual theory. Again, I'm agnostic about that. I'm just trying to set up systematically charges and fluxes. So it will be very familiar to all of you that there is an analytic continuation from ADS to de Sitter. So in particular, if you start from the Poincare patch and you analytically continue with the radius and you swap the roles of radius and time, you go from the Poincare patch of ADS into the Big Bang patch of de Sitter. Yeah.
Just to make sure I'm on the right page. So in the previous picture, the picture showed outgoing radiation, but
Yes.
genuinely it's very hard to distinguish whether it's outgoing, ingoing, and so
Yes.
actually is
So
there.
sorry, I should have said.
Yeah.
So that's a good question. I'm actually showing a picture in terms of outgoing. I could equally have been having ingoing radiation as well. Yes.
Yeah. And actually, is there any result in the literature about some sort of positivity? Is there? Do we
Yes.
understand any?
Okay, so positivity. So there are certain results which I'll come to in certain frameworks. So the analog of bonding mass formula, for example, there is a formula in the context of, say, Robinson-Chapman spacetimes that if we ask about the change in charge between C1 and C2, a charge which is associated, for example, with a vector which asymptotically becomes a time-like killing vector, right? That actually has a monotonicity property, right? So that has a monotonicity property. So there are results of that nature in the literature. Positivity, one has to define it a little bit, right? But that would actually link into results associated with positivity when things have settled and become stationary. But actually here, I think I'm particularly focusing on fluxes, so I'm asking about the changes of charges, right? Rather than the absolute value of positive and negative. But then if we actually define that there's an extremum and that's the lowest it's going to be, that would be where the positivity comes into it. Yeah. Positivity, it depends on how we set up the problem. And for so far, I've been quite agnostic about G0 and so on.
Okay, thanks.
Okay, so I'm doing analytic continuation from ADS to de Sitter. And, as I think is familiar to everyone, when you do this analytic continuation, so Poincaré coordinates, of course, only cover a patch of ADS. Similarly, the Big Bang coordinates only cover a patch of de Sitter. So the coordinates cover only half of de Sitter. And the way I've set it up, tau goes to infinity is future infinity. The coordinate horizon is now at tau goes to minus infinity. I could equally have done an analytic continuation to cover the other half of de Sitter, which would have linked to the past infinity in de Sitter. So if you do this analytic continuation, you obtain what people would call the Starobinsky expansion. So as you go to the future infinity or the past infinity of de Sitter, you get the same kind of expansion that we have for ADS, but now we've exchanged the rule of radius with time. And so, this means that the volume, the radius divergences that we had for ADS have now been associated with the time divergences that we have for de Sitter. So the main thing that we learned from ADS CFT, ADS going over to de Sitter, is how to deal with those divergences in time. Now, when you do this, although I call this a Starobinsky expansion, it's strictly not a Starobinsky expansion, in the sense that when Starobinsky wrote this down, he was almost entirely interested in the case that the G0, which is the non-normalizable part of this metric expansion, was just flat, right? So he was interested in what we would call asymptotically de Sitter, whereas again, I can be agnostic about it. So for me, G0 is a generic three-dimensional Euclidean metric. It needs to be non-degenerate, but I don't need to be making any other restrictions about it. G2, as ever, is determined in terms of G0. It's just the Shelton tensor. And then G3 is the normalizable piece. So G0 and G3 are the conjugate pair. G3 is the normalizable piece. And we will see, as you would expect, that G3 is actually capturing essentially the state you're in. It's capturing charges and fluxes. Okay. So, again, this analytic continuation has been around in the literature since almost the beginning of ADS CFT. This is not in itself new. The thing I'm highlighting here is really the fact that we can have a non-trivial G0. Okay, so having said that, if we take a step back and we consider just asymptotically ADS and asymptotically de Sitter. So asymptotically ADS is when we have, so that is the case where we simply have a conformally flat boundary metric. G0 is Minkowski, and so if we're looking at the group of conformal Killing vectors, that's just the conformal group of the boundary. So we compute charges which are associated with time translations, boosts, rotations, etc. For asymptotically de Sitter, G0 is just the flat Euclidean metric. And so the relevant symmetries we have now are spatial translations, spatial rotations, and we still have a scaling transformation, right? Because we're looking again at the conformal symmetries, we still got a scaling transformation. So the claim is that if you're going to do something with charges in de Sitter, you should look at the things which are real charges, conserved charges. You should think of the things which are the asymptotic symmetries. And the asymptotic symmetries are these things, right? Spatial translations, spatial rotations, scaling transformations. So sure, there's no time-like Killing vector anywhere. We're not going to have a mass associated with a time-like Killing vector, but we will actually have charges associated with these particular symmetries.
That depends on the foliation.
Sorry, at this point, it doesn't depend on the foliation because I'm going to be looking at charges. So it doesn't depend on the foliation in the sense that I'm going to be interested in charges which are associated with future infinity. The point about non-trivial horizons and so on will come through in a moment in the sense that we cannot, in general, assume that we're actually going to have conserved charges at all. We will typically there will be non-conservation issues. Yeah.
But why isn't this SO1?
So these are the symmetries of asymptotic de Sitter?
Just the basics and by
Yes.
you get them all.
That's right. Yes. Sorry, that's all we get. So I've just given you examples. Yeah, so this is, I've chosen to represent in particular coordinates, but there's, I can mix them all. Okay.
Your theta was the power of the previous slide. Is the midline kind of thing?
That's right. That's right. Yes. Yeah. Okay, so
But those are not those are subset because you have spatial rotation, spatial translations, and then scaling transformation. But again, so you're keeping one slice fixed.
I'm not keeping any slice fixed. I'm asking what is the symmetry of the conformal boundary, right? Which is just flat three-dimensional space.
By this you mean really the isometry, it's not the conformal isometry.
I mean the conformal isometry. So I agree, I haven't written down the whole group here. So I've given you the scaling transformation, but I haven't given you the special symmetry. Yeah, I've just given you examples, yeah. To be honest, the point of this slide was simply to emphasize really the middle line, which is that actually the analog of the usual Minkowskian symmetries are simply the Euclidean symmetries. So they're spatial translations, they're spatial rotations, and those are the things to which we should compute charges with respect to. Yeah.
Does this recover also 1.4 and what about your boost symmetry? Does this recover also 1.4?
So it will recover SO 1.4, yeah? Yeah.
So it includes boost symmetry also?
It will do, yes.
Okay.
Yeah. Okay, so that was for asymptotically de Sitter, right? So for asymptotically de Sitter, we have these asymptotic symmetries which correspond to conformal Killing symmetries of the boundary. But the key point is that what we're doing applies to spacetimes that are not just asymptotically de Sitter.
We can have
a boundary metric which is generic and has no symmetries. And as I said before, almost all the prior literature across the GR community, so Ashtekar and collaborators, Krischel, assume that we've got a flat boundary. Not only is this unnecessarily restrictive, we would claim that when radiation is present, it's necessary that the metric has to become spatially dependent. And so actually, if you look at this picture here, you start to see why. So we'll start building up these pictures. So in this picture, I'm showing that the horizontal line at the top is Scri plus, so that's future infinity. And I'm thinking about rotating from ADS. So in ADS, I was considering space-like slices. Essentially, we've swapped the role of space and time. The natural codimension one slices on which to start defining charges and fluxes are time-like. So the red slices are time-like slices, and they are, you know, C1, C2, they're different time-like slices. So the natural thing to do when we're starting thinking about charges is to put these charges on time-like slices. Now, the other thing that comes in, which is the thing that I thought Massimo was asking about, is that actually, because we're thinking about time-like slices, we have to worry not just about the future, but also about the past. Now, if we have horizons present, we may actually want to terminate these surfaces at a horizon, and that's been done quite a lot in the literature, particularly Ashtekar and Krichel were often doing that. Here again, I'm being a bit agnostic about this. What I'm going to do is say that actually I'm typically going to consider an endpoint to see in the past. And so in the shaded region here, I've shown one end being at future time infinity, and I've shown the other part ending at finite t. And again, for me, I might tilt that so that's actually ending on a horizon, or I might be able to extend it all the way into past infinity. Now, this sort of piece that actually you really had to think very much about both endpoints, so not just the, you know, future infinity, whether that's the, you know, future infinity or past infinity, but you had to think about where the slice ended. Again, was something that hadn't really been understood in the literature. So previous literature on charges, actually, it almost, if you go through the literature sort of paper by paper, it implicitly assumes that contributions from these inner sort of boundaries of surfaces vanish. So when people do analysis where they're taking de Sitter and they're putting linearized perturbations, they typically do this by putting fall-off conditions on the linear perturbations. They basically make them fall off with time, so that contributions from any interior surface which is sufficiently far back in time would vanish. What's the problem with this? Well, the same problem comes as with imposing that the space-time is asymptotically de Sitter. The more you accidentally impose conditions, the more you've restricted your physics. And so actually, if you sort of say that, you know, fall-off conditions, you put fall-off conditions on fields, you're basically excluding some kinds of physical processes. And our claim, which is sort of backed up by the analysis we do of spacetimes like Robinson-Troutman, is that sort of the generic kind of situation that you would have, both in sort of, you know, the formal analysis we do, but also actually in analysis of gravitational waves, is that you really do need to take into account contributions from the inner surfaces. That's a kind of generic type of behavior that you need to take into account.
The endpoint in the past, your analysis being experiment.
So I'll come to that in just a moment. So at the moment, I'm agnostic about it. So I've just said I'm gonna close it at t, and it might be that it can go all the way into square minus, but you know at the moment I'll just say it's at t. And what I'm saying is that in the literature, people have usually, even when they put this at finite t, they've just imposed boundary conditions so that everything vanishes. Yeah. Okay, now coming to Aurora's question. Suppose we do try to consider slices that go all the way between future and past infinity. I think the summary of this is that life is very boring in this case. Because actually, if you insist on having a space-time where a de Sitter space-time where slices can go all the way between future and past infinity, you're effectively forced into a scenario where the charges are associated with a vector which asymptotes to a conformal killing vector near both the future and the past infinity. Okay. And that's quite restrictive because again, if we think about, you know, in the middle of our space-time, some kind of, you know, black holes colliding, forming gravitational waves, typically it will be the case that it would not be reasonable for the bulk vector to be a conformal killing symmetry both in the future and the past. But if we have this situation, just as for the ADS case, we can show that the integrability criterion is satisfied and the conservation criterion is satisfied. So what that's going to mean is that charges associated with C1 are the same as the charges associated with C2. To calculate those, we're going to use the asymptotic expansions near the past and future infinity. So we've got these expansions. I should say here, just for technical sake, I've actually exchanged my tau for an exponential of minus t instead. So just for sort of simplicity. So I can use the asymptotic expansions of the metric and the corresponding expansions for momentum. And I can show you that the integrability condition is satisfied if the vector that I'm considering is an asymptotically conformal killing vector, and then there's a technical condition on the third component, the term which is the third term in the expansion of the momentum, if that trace is 0. Now, that is something which probably looks very familiar to many of you. So the fact that the third term in the expansion of the momentum is 0, that's the same condition as the conditioning of the vanishing of the conformal anomaly in the dual three-dimensional CFT. So it's exactly the same condition. And the fact that that holds comes from the fact that if you take the ADS4 asymptotic expansion, you do the analytic continuation, the de Sitter for asymptotic expansion inherits analytic properties. And indeed, this particular trace vanishes. I said to you I was going to be agnostic about whether there is a dual CFT for de Sitter. And that's why I'm carefully not framing it in terms of a language of a CFT. I'm just saying the trace of the third component of the momentum vanishes. And if that's the case, then these, if we've got an asymptotic conformal killing vector, the integrability conditions are satisfied. That means that we can integrate to get the charges. And if we've got such a thing, then we can just write it up in this particular form. So the conserved charge is the contribution. So we've got two contributions because we've got two endpoints to our slice. So the wall charge is the contribution from future infinity minus the contribution from past infinity. And again, we're writing this in exactly analogous condition, in exactly analogous way to the way we wrote it for ADS. So the charge is written in terms of the conformal killing vector at the boundary, and then the third component in the expansion of the metric near the boundaries.
The pi, it's a very basic question. Isn't that pi non-zero for particularly particle in the future and in the past and the inflationary?
Okay, so pi is non-trivial. The trace is 0. So pi is in general non-trivial. Yeah, it's just the trace which is restricted. So the Einstein equations are force that the trace is 0. Yeah. So it will be generically non-trivial. Okay, and so we can work out this charge. And again, it gets two contributions, one from the future and one from the past, as you would expect. And then we can actually show, using the same analysis that you would have for ADS, that this is conserved. So as you go between these two slices, that the Q's on slice 1 are the same as the slice on Q2.
One thing, I'm not sure that you said anything that is different from that, but just to make sure I understand. So in the difference when we rotate back to ADS is that if you draw this Cauchy slice in ADS, it's capturing everything that is happening in the bulk at any radius.
Yeah.
Whereas here you can imagine having an observer which is time-like and massive that just propagate outside your strip.
Yes.
You would have a non-trivial physics. You would not be able to capture it unless it radiates inside your region. Is that correct?
That's right.
Okay.
That's right. That's right. So that's the next slide. Okay.
Regarding pi. So the metric, in inflation, the metric is 1 over, say, eta squared, and then the flat metric. Let's say, then in that case, the pi, even trace of pi is on scale. The relative respect to conformal times minus 2 divided.
Okay. Right. So let me come to a couple of points here. So I said at the beginning that I was restricting to Einstein gravity with just a cosmological constant. Of course, if you start adding scalar fields here, just as you do in ADS, you can actually have scalar contributions to the trace, right? So you just modify these expressions, but they will be suitably expressions associated with them. And they will not spoil the fact that you actually have, sorry, I don't want to jump around too much, but they will not spoil the fact that you have integrability conditions. So we can do everything I'm doing here in the context of real, inflation with a scalar field, but you will have scalars coming along in some of my formula. Okay, so hopefully that piece helps.
So that's not the pi of the background.
No. No, absolutely. That's right. Yes. Yeah. Okay. So if we are in something which is asymptotically de Sitter at the future and past, we indeed have conserved charges but these conserved charges are associated with these time-like slices. So I'm going to give you in a moment examples of these for de Sitter-Schwarzschild, which is the obvious case that you would think of. But of course, this is highly restrictive. So this already came from the question. So most of the times in a cosmological constant, we're really not interested in the case where we have, full symmetry at past infinity and future infinity. We're actually interested in the case, again, particularly in the context, whether it's inflation, whether it's gravitational waves, where we've got some kind of non-trivial gravitational radiation coming in. And in the presence of radiation, it cannot be the case that we will have an asymptotic conformal killing vector. So in this picture, the green radiation, it hits scribe plus, right? And when it hits scribe plus, we've got spatial dependence. So it's not an asymptotic conformal killing vector. And now what we would do is instead say, actually, the change in charge between Q plus is going to differ from the change in charge between QT, between the two surfaces, in terms of the net amount of radiation going through it. So we're going to do a flux. We're going to look at the fluxes and see how charges change. Okay. And again, I think until a few years ago, this was sort of not entirely brought out in the literature because people had, always been considering the case, at least when they were doing formal charges, so the Ashtekar and et al. Literature, they were always considering the case that they insisted that at scribe plus we absolutely had conformal killing symmetries. So what do? Well, we consider the case, as I said, that we do not assume that there's an asymptotic conformal killing vector. We can actually, again, we might insist that it's a localized burst of radiation. So there's an asymptotic conformal killing symmetry apart from certain parts of this boundary, but we do not insist that it's an asymptotic conformal killing vector. And what we do is we write an equation for the flux. So we can work out the equation for the flux, and there's an analogous result both for the flux going at future infinity and the result at QT. Okay. So now let's illustrate this with a couple of examples. So Schwarzschild de Sitter. So hopefully sort of familiar metric written down for you there. And this is written, I've expressed it in the way that the metric is written in the future patch. Now, this clearly fits into the initial framework discussed because there's no gravitational waves. This is something which is something for which we would expect to have asymptotic symmetries. And indeed, when we plow through this, we can find that. So the future patch, you should think about the region which is shown to the top right. And you should think of our charges as being associated with the time-like surfaces which are shown as blue lines. So what we're saying is that we compute charges associated with those surfaces, and they are conserved as we go through them. Okay, so if you take Schwarzschild de Sitter, you switch to these Pfeffen-Graham or Sarabinsky type coordinates, you indeed find that the metric has a non-trivial term at the third order. The only parameter you've got is n, so remarkably enough, it's proportional to n. And then when you work out what charges you've got, there are non-trivial charges which are associated with spatial translations and with conformal transformations. So those are both proportional to m. Of course, we haven't broken rotational symmetry, so we don't have charges which are associated with those. Okay, so these are very well-defined charges which you can define for Schwarzschild de Sitter. And as I said, they're associated with these time-like surfaces. Now, if you want to get a little bit more fancy about this, the Kern-Nut solutions, I'm not saying these are of enormous physical interest, but they are beautiful mathematical examples discussed by Plavansky and Leniansky. So it's 3-parameter family of solutions. We don't have fluxes again. Of course, everything's expressed in terms of the 3 parameters. But the thing that is interesting here is that, as ever, when you have a nut parameter, which is here L, the space-time is only asymptotically locally de Sitter. That's because of the nut vibration at the boundary. So the boundary is no longer flat, it's actually vibration. And so it goes beyond the previous analysis of charges. I always put this slide when I talk in Cambridge and places like this, because people try for many, many years to define charges from nut solutions, right? So the fact that we can do that, they get excited about. Everyone else says, well, we don't really care, but, it's just a technical interest. But, we can do those cases.
So in this example, what's the topology of the boundary then? Do you know? You said the topology is non-trivial. Is it what you said? Or?
Yes. So you should think about it as an S1 non-trivial over the S2 rather than being topologically S3. So it's simply that. Yeah. So I mean the asymptotically de Sitter would just be a spherical boundary, right? When you can formally compactify it. So here we've got a non-trivial S1 vibrated over the S2 when we've got nut-type solutions. That's what we've got.
Okay, so
yeah,
so it's S3 with the up vibration or something.
That's right.
Yeah. Okay.
Yeah, squash spheres basically. Squash spheres. Yeah.
Since you are defining charges on these time-like hypersurfaces, would it be natural to associate them with, let's say, the world line observers that define static patches?
Yes, it would. Absolutely. In some sense, this is trivial in this particular context, right? Because in any case, we've got symmetries. What you're describing becomes non-trivial in the context that we're just coming to, where we start to say we don't have asymptotic symmetries anymore. So how do we choose the vector fields? And the vector fields can naturally be associated with the world lines of observers. So the answer is yes, but in this case, it's kind of trivial. Okay, so now let's come to a fun example. So I'm just going to sort of flash this up rather than talk through it. Essentially, the Robinson-Trapman de Sitter solution is an exact solution which is characterized in terms of a solution to the Robinson-Trapman equation. So this is a family, although people refer to it as the Robinson-Trapman solution, it's a bit of a misnomer because it is a family of solutions. And the family of solutions, the key point, you don't care about the formula, is the key point is that these solutions asymptote Schwarzschild de Sitter. Okay. So depending on the function, they will asymptote more or less slowly, but they are exact solutions. So of course, the Robinson-Trapman solutions, by definition, include Schwarzschild de Sitter itself. That's a trivial, well, not trivial, but that is, a reduction of the solutions. But for a generic function satisfying the Robinson-Trapman equation, we have non-trivial gravitational waves. I think it's more rather than going through the properties of the function, I think it's better to illustrate it with this particular picture here. So the Robinson-Trapman solutions you should think of, so what we're showing here is the horizons, we've got non-trivial horizons, and I'm showing the sort of in the top right region, the asymptotic future infinity. I'm showing the box region that I'm considering. So I'm going to be considering charges in that box region. The red are the time-like slices. And then I'm showing gravitational waves. I'm showing fluxes which are coming through those. And then the statement is that as you go further to the right of the diagram, this is actually settling down to be Schwarzschild de Sitter. Okay, so that's the kind of feature. So Robinson-Trapman, they are, complex solutions. The actual nature of the equation, if we just flip back to it, it's a non-trivial defining equation for this defining function P, as you can see. But it has this really nice physical interpretation. I'm gonna come very next slide, actually. Okay, so this is a very nice toy example for us because in this particular case, we're going to choose the box region as I've shown, and we're going to see that we're actually going to have non-trivial changes between the two time-like slices, which relate to the flux of radiation which passes through those. So what we can show is the following. So in this case, and it links actually, I think, a little bit to the question, there are some natural choices of vector fields. So we're going to choose a space-like vector field, which is going to asymptote to a Schwarzschild killing vector. And it's actually, you can think of this also as being associated with distinguishing between different families of time-like observers' orbits, right? So you can think of it that way. And then what we can see, we can write down an expression for the Q, the charge at future infinity. And the really interesting thing is that we can actually show, using a flux formula, a monotonicity property. So in particular, what we're showing is that as we move to the right of my diagram, a monotonicity property of how the Q changes. Okay. And the vector field is chosen, as I said, to asymptote, because as we're asymptoting to a Schwarzschild black hole, we're going to choose that vector field to sort of smooth the asymptote to it. Clearly, that's not a unique choice, but actually we're just capturing that flow into, we're capturing that transition into a Schwarzschild black hole. So we've got a nice monotonicity property. We've got other properties as well, which I'm not going to go into. Okay, so this is a summary of this part. So take-home messages. Wall charges are naturally associated with time-like slices in de Sitter spacetimes, but generically in cosmological spacetimes, you will not, you will be interested in having gravitational waves, gravitational fluxes. You cannot have boundary metric being conformally flat because the radiation will hit there inevitably, and it will mean that it's not flat. We can calculate the fluxes associated with suitable vector fields and demonstrate suitable monotonicity properties, which we've illustrated in the Robinson-Troutman case. Okay, so my final few slides are around other asymptotics. So let's go back. The left-hand slide you've already seen, the left-hand picture you've already seen. So that is ADS with flux going to the boundary. The right-hand side now I've shown asymptotically flat. And the key formula that we're using throughout in talking about the fluxes is this variation of between C2 and C1 and expressing it in terms of omega. So asymptotically locally ADS, again, in the presence of radiation, that boundary metric is generically not conformably flat. And if we go back to the example explored, starting from 10 years ago, the ADS Robinson-Troutman, which is the same metric I just showed you, but flipping the sign with cosmological constants, again, you can compute fluxes associated with the vector field, which asymptotes to a Kenning vector in the future, and we again get suitable monotonicity properties. An interesting point is in the Robinson-Troutman example, you may also, even in the ADS case, want to consider putting an inner boundary here, so an inner boundary to C2 and C1, and taking into account inner radial boundaries of the box region. Okay, now the point which is possibly interesting for people in this room. So what are we doing at the moment? So this is just to sort of signal some things which are going to be coming out in the next couple of months. So start from the non-zero cosmological constant case, take the lambda goes to zero limit, moving from Pfefferman-Graham gauge to a suitable gauge, Bondi and U-type gauge. You then obtain asymptotically locally flat spacetime. So I know many people in the room have been, have worked on this. So the key distinction that we have compared to the past literature is the following. Because we had very generic boundary conditions for asymptotically locally ADS, asymptotically locally de Sitter, we have a more general Carolian structure for our 4D spacetime. So in particular, we of course have a non-vanishing cotton tensor when we do that. So we have that piece, but also, although I've suppressed all the discussions and all the details throughout this, we were implicitly renormalizing everything, right? So we dealt systematically with the divergences all the way through. Implicitly, we were using that the Papadimitriou-Skenderis approach to holographic renormalization. Inherently, the resulting charges and fluxes that we get are renormalized when we do that. So again, that's kind of nice and elegant. So again, the big thing is that we actually get a more general class of boundary structures than has been seen associated with asymptotically locally flat spacetimes. Now, what can we do with that? Well, the first thing that you do is you try to make sure that you recover the results that you have to recover. So in particular, if we were talking about this in the asymptotically flat case, if we're actually talking about, so take my slice C1 and C2, and we're actually talking about changes, we've got radiation coming out, and we're talking about changes as we go between C1 and C2. The first thing that would come to mind here is things like the Bondi mass formula. And indeed, we recover, as we have to do, the Bondi mass loss formula as a special case, but we also recover the more recent discussions of things that we heard, right? So we're making sure that we cover those as well. It's still the case that examples such as Robinson-Troutman are quite useful. So the Robinson-Troutman is a case where we actually have, again, in the far future, it is asymptoting to a stationary black hole. And so you're actually sort of choosing your vector such that it actually asymptotes to a symmetry. And that's quite, that's a useful, and we're obviously recovering the sort of well-known results associated with Robinson-Chapman in that case. Okay, so that's where we are so far. This is one of the first talks of the summer. I think many of you will be in the Edinburgh meeting and other meetings, so expect to hear more details about this over the next few months. Now, where are the subtleties? So I'm not claiming that we have solved everything in one go. We do inherit renormalization, systematic renormalization from the zero cosmological constant limit. It is more subtle as ever in odd spacetime dimensions. So the usual issues of finite contributions from finite counterterms comes into play. We evade, it wasn't an accident I mentioned that we were using the Papadimitriou-Skanderos approach to renormalization, where you effectively, all you do is demonstrate that the counterterms exist. You don't need the detail of explicit structure. In odd space-time dimensions, we do need those, and that actually translates into understanding what are the appropriate, well, effectively, we have to work out what is the structure of counterterms which is consistent with the Carolian structure, right? So there's definitely more to do on that one, just to be transparent about that. The other thing which we are only sort of partially at is the following. In ADS-CFT, you interpret the pair G0 and G3 for solutions such as Robinson-Chapman in terms of the CFT background, the CFT state. In Robinson-Chapman, I said that at late times, it approaches a black hole. It goes through a hydrodynamic phase, right? So at that stage, G3 actually behaves, it captures hydrodynamic properties, as many in this room have explored. And so there's a question here, do we get the same emerging? So the G0 and G3 translate over into the corresponding Carolian terminology, but can we interpret the piece there in terms of Carolian hydrodynamics, for example? Again, that's an open question. We haven't, it has to work, but we haven't done that. The other thing that we haven't worked out, so again, touching on the talk that we had yesterday, the discussion of these higher memory effects. We have more general boundary conditions, right? We're asymptotically locally flat. How does that translate into things? Again, we haven't started thinking. What we've been focusing on so far, as I say, is recovering all of the standard results that we have to do in terms of monotonicity of fluxes and so on. We haven't actually started to look for additional consequences of what are more general boundary conditions. That was the last slide, so thank you very much. Apologies, rushing through it.
Thank you, Marika, for the very nice talk. Question?
Yeah. So I have one comment and one question. So at some point you said that Abhay and Piotr put the conformally flat boundary condition on the, I think that is not maybe understanding why it's a little bit misinterpreted, because neither Abhay nor Piotr did put the conformally flat boundary condition. What we did conformally flat boundary condition to the background. Then all the fluctuation is contained in the linear H-Barter wave.
I completely agree with that. I do agree with that. At the same time, you don't need to have it for the background. Yeah. So I agree with the refinement, and I promise we'll refine it. It is refined more carefully in the paper. Yes.
So they put the conformally flat boundary condition on the background. So on all the fluctuation
I appreciate, but what I'm saying is we don't need to do it in the background.
Yes,
I do completely appreciate that when the perturbations were considered, these didn't respect that. I completely appreciate that. Yeah.
And other question is that if you, so at some point you said that this monotonicity property of Robinson-Chapman, and can you just write down a mass loss formula from the Bondi Sachs? Because I mean, by now we understand the mass loss formula, at least for de Sitter and de Sitter also.
Okay, so in this particular context, so when I presented this formula for de Sitter, remember we don't have mass in de Sitter, right? What we have is these charges which are associated with different symmetries. Now, you're absolutely right that when we phrase it in terms of ADS, where we have asymptotically a time-like killing vector, we would be able to interpret the particular choice of psi, which asymptotes to the time-like killing vector, in terms of a bonding mass loss type formula. And that was, that's already been done in the literature. So you would interpret it. In the case I presented here, again, it's not a mass per se because there's no time. It never asymptotes to a time like here. So
Yeah, I mean,
but it still plays the role, as you see, we said here, it plays very much the same role as a bonding mass loss. This is the analog for rotating de Sitter. Yeah, that's the same.
Or more explicitly, can you write this Qi in terms of boundary variables? So I want to just write delta Qi in terms of boundary variables.
You absolutely can. Yes. Yeah, you can do so.
And that is a negative definite?
Well, I mean, this is going to be negative, this particular quantity is going to be negative semi-definite. So, it's simply a translation into writing it into different variables. Now, interpreting it, and thinking of other identities, that's
okay, thanks.
First of all, thanks for the very nice talk. I was wondering, this renormalization that you are saying it's inherited from, just taking this lambda going to zero limit, what happens at the I naught point where, these asymptotically locally flat boundary conditions will...
So I could have actually had a fourth point here, that I0, I plus and I minus still remain subtle.
Okay.
So I was having a conversation this morning that actually the behavior is I plus. For these particular issues, for these particular discussions, I plus is not an issue. The long-standing questions of how do we approach I0, we are not claiming to have anything new to say about those at this stage. So that could have remained there as well.
Yeah, because
in some sense, I think it's possibly helpful to look at this particular picture. What we're saying is that we can actually sort of look at a delta Q between C1 and C2. And now your question is, what happens as C1 approaches really I0? That's one way of framing it. I'm saying, well, actually, I'm also worried about what happens as C2 subtleties as C2 approaches scribe plus in some contexts. Are there some divergences? Those are subtleties which we do not claim to have resolved. And long-standing issue of how you link the asymptotic analysis near scribe plus to the approach to I0, the whole math literature associated with that, we don't claim to have anything new at this stage. This should be helpful, but we don't claim to have anything new.
Typically, you would expect some divergences with this asymptotically flat boundary conditions that I don't know if it can be. This is linked to the problem of seeing super translations, differs to super rotations, differs to, and all.
So I think the statement is at this stage we simply don't have anything new to add to that. If I was to sort of say a corollary, if you go back about 25 years, people tried to do the analog of the Pfeffer and Graham analysis specifically around I0, as some of you may know, and found non-locality associated with that. We have nothing new to say to that. So we're sort of saying we're doing the analysis, close to scribe plus, we're taking it from the limit. We're not actually approaching that point yet.
Thank you.
So it's still stuff.
Are long-range interactions included here?
Sorry,
the long-range nature of interactions in flat space for massless particles? Because I would imagine that if you take the limit from ADS, it may be tricky to.
So all the subtleties that we have encountered so far, we have been able to solve. Some of the things which I think you're getting at probably kind of come into the top bit here, right? So that will come into play. Of course, people in the context of correlation functions where they've got renormalized correlation functions, they've managed to take the limits of those, Pack-Rouse and co, Costas and co, and so on. But there are probably still subtleties to do it. So we're not claiming we've taken one separate.
I'm asking because in flat space there's this long-range lead time divergences.
That's right.
And
that's right.
They're a bit different as far as there are new charges associated to those.
So that, and I think that was exactly my point about saying I don't think we've nailed what happens at scribe plus. I think we were actually talking about this morning. I think what we're doing effectively is looking at quantities which are not susceptible to the, do not include these kinds of contributions. We're effectively, not including those so far. So I think I think that's my best guess. We're evading it, but as I was saying this morning, you know, in conversation, there are certain calculations where we certainly have sort of, you know, things which would be divergent at later time, where we still need to understand how to resolve those. So again, we're not sort of saying sort of that aspect. I should say actually, just to sort of pick up on this, of course, if you're looking at quantities such as the delta Q between C1 and C2, by definition, even if there's some diversion at late time, if you're looking at the delta, it won't come into play there, right? And that's why we're safe for what we're doing. If we look at sort of absolute values and so on, that can be a subtlety. If we start pushing C2 off into the far future, that can be subtlety. So we're not claiming to have resolved that yet.